So I've seen a mass on a spring now and solved it to death. The fun thing about simple harmonic motion is that you can find lots of different equations that give you simple harmonic motion, and as soon as you've written down the differential equation, you can say straight away what the frequency is based on the physical parameters of the system. I'm going to give you a couple of different examples now. The first is oscillation due to a buoyancy force. So imagine we've got something floating in the water, and it can bounce up and down in the water. It's got some mass m, and at the surface of the water it's got some cross-sectional area A, and y is in the positive direction. So if we change the depth of this object, it displaces a volume of water, which is A times y, the cross-sectional area times the amount it goes up and down. We're assuming this section here as a constant area. And so this gives a mass of water, which is the density of water times A times y. And so the buoyancy force is negative g rho A times y. That's something which you can calculate. And so this is now the force due as a function of the displacement y, but we can use now that the acceleration is equal to, or mass times acceleration is equal to the force. And so mass times acceleration in y must be equal to this force, which gives us y double dot is equal to some constant times y. Now this looks exactly the same as the equation we had for a mass on a spring, but instead of k on m here, we've got g rho A divided by m. But if we used our trial solution with omega, we would just find that this thing here must be equal to omega squared. And so the frequency of the motion, or the square of the angular frequency of the motion, must be equal to all of this. Same equation. We identify the constant in the differential equation, and straight away we know the frequency of the motion. Another example is a swing pendulum. Now, mass on a spring is really great because it gives you a linear differential equation. A swing pendulum is more common, but to find an equation where we can really say it's simple harmonic motion is a little more complicated, because this equation is not inherently linear. So let's go through this. This pendulum is attached to a point here, so this pendulum bob here is going to be doing circular motion around this point here. So the radius of that motion is this length L of the string, which we assume has no mass. The mass of this pendulum bob here is m. The force due to gravity is mg. We break the force due to gravity up into two components. The interesting component to us is that which is perpendicular to the string, that is mg sine theta, and this is the force that is applying a torque to this mass. If we have a torque, we have circular motion, we're going to use angular equations of motion. So in angular systems, force equal to mass times acceleration becomes torque equals to moment of inertia times angular acceleration. Now the torque in our case is the distance L multiplied by this force, so the torque is negative mg L sine theta. The negative sign here comes because the direction of this force is in the opposite direction to the angle theta. The moment of inertia is given by ml squared, assuming this is a point mass on the end of our string. And so this gives us an equation that torque is equal to negative mg L sine theta, and that is equal to ml squared theta double dot, giving us this equation of motion here. Now this is not a linear differential equation. There is no analytic solution to this. The problem is the sine theta. Now for small angles we can get rid of sine theta because it's approximately equal to theta, and so this gives us an equation that looks like this. Now this is the same equation that we had before. We could rewrite this in terms of x as well if we wish, and we see that the frequency squared here must be equal to mg on L. So again, just from doing the physics, we can straight away say what the frequency or the angular frequency of the motion is. It'll be different each time because the physics is different, whether it's a swinging pendulum or something bobbing up and down the water, or a mass on a spring or an electrical circuit or whatever it is. But as soon as you have this differential equation of motion, you can say what the frequency is in terms of physical parameters. So I'll finish this video with an example of a swing pendulum that is definitely not in the small angle regime. It's being used for extreme cruelty. Please don't do this to each other. And I'll see you in the next video when we talk about waves.
Maybe somebody else should just go. 2, 1, 0!
I can't do it.
2,
1, 0!
I don't even want to jump.
2, 1, 0!
I don't want to do it.
3, 2, 1, 0.
I don't want to do it.
Put the other hand on the rope.
Honey, I don't.
Take a 6-inch step to the right. Just not right there on the edge. Just like that.
Honey, I don't want to do it.
Put the 2 hands on the rope. You know I love you, right?
Oh, please don't push me off. Please
I'm
don't.
right. I am not. I'm right here. I'm right here. I'm not going to push you. I'm not going to push you. But if you stand here for more than 10 more seconds, I will. 3, 2.
Honey, honey!